So the our solar system is essentially made up of the sun and everything that orbits around the sun. Okay, so the sun is a star. It's not a big star. It's not a little star. It's a fairly average size star, and it's right in the middle of a star's life. So it's just like the average of a star is in terms of comparing it. So the sun is huge, bigger than you think you can imagine. It makes up 99% of our solar system's mass. So we've talked about mass and we've talked about weight and that kind of stuff. So the amount of matter, right? And if we look at our solar system, the matter in the sun, in other words, what the sun is made up of, consists of 99% of the matter in our solar system. You take all the planets, all the asteroids, all the comets, all the moons, everything combined, and that's 1 out of 100 compared to the size of the sun and the size of the mass. The sun is massive. So the solar system, again, consists of the sun and everything that orbits around. That includes the planets, their satellites, which is another name for moons, the asteroids, and comets. So we're going to talk about those different components today, and then we're going to do some practice questions and then call it a day. Okay? So our solar system has 8 planets that orbit around the sun. They're broken up into essentially an inner group of planets and an outer group of planets, and that's because they're kind of clumped. There's a huge gap in between the inner and outer planets. So the inner planets are all kind of clustered pretty close together, and close, relative term when we're talking about the solar system, right? Because they're very far away, but relative to the size of the solar system, the inner planets are close to the sun and close together. And they share some similar properties, as well as the outer planets. The inner planets, we call and refer to them as the rocky or solid planets. In other words, they're made up of solid rock, and they are relatively small when we compare them to the outer planets. So that would be Mercury, Venus, Earth, and Mars. Those 4. All right. The outer planets, we call them the gas giants, and that's for exactly the reasons it sounds like. They're made up of primarily gas, and they are very, very, very big. Okay? And that would be Jupiter, Saturn, Uranus, and Neptune. We'll go into some more details in details of the planets in just a second. But lastly, the other thing to talk about would be our moon and how it works or how it orbits. So we know the Earth and all of these other planets are orbiting around the sun. In very much the same way, our moon and other planets' moons are orbiting around those planets. And those orbital paths are dictated by gravity. So the sun's gravity is huge because it's made up of a lot of mass, and the size of a planet and more specifically the mass of a planet dictates the amount of gravitational pull that it has. So when we start to look at this chart that I'm going to pull up, you'll notice that the bigger planets tend to have a lot more moons, and that's because they have a stronger gravitational pull. All right. Our particular moon orbits around Earth every 27 days. So 27 days is the cycle of a moon, right? So when you go from full moon to crescent back, or to new moon to crescent back to full moon, that cycle is 27 days. And what you're seeing is basically the proportion of its surface that's in shadow compared to, like, as we see the moon, it's not really going away, right? It's just a larger or smaller proportion or portion of it is in shadow versus in light. So it's kind of how it's positioned relative to the sun and the Earth. So I'm going to stop this Let me see. Yeah. So I'm going to stop this here, and I'm going to pull up a chart that I think you'll find interesting. I think it's interesting. So this chart here is one I like to kind of break down. And so it shows, obviously, all of our planets. And then it breaks it down into, obviously, the name of the planet, the distance from the sun, the diameter. So if we remember from our geometry days, diameter is, if we're talking about a circular object, right? In this case, we're talking about a sphere, a three-dimensional, right? Diameter would be the distance from one point of the circle to the other point through the center, right? So that's the diameter. The diameter of the planet, the number of moons it has, its rotation period, which is a fancy way of saying how long a day on that planet is. So when we think about Earth, the Earth is doing two things. First, it's rotating on its axis, so it's spinning. But it's also orbiting the sun. So it's spinning and it's orbiting, like this, right? So it's constantly spinning, 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 and orbiting around the sun. So think about the difference between those two things. Rotation period is the amount of time it takes that planet to spin around its axis. And a revolution period, which is the last column, is how long it takes it to orbit around the sun. In other words, what we call a year, right? So if you look at Earth, so let's start with Earth. Earth is 93 million miles from the sun and has a diameter of almost 8,000 miles. It's almost 8,000 miles across, 7,923 miles. So if we, and again, I'm going to go through these one at a time, but if you notice, so here's the break, right here between Mars and Jupiter, between the inner and outer planets. So you can see there's a stark difference in distance from the sun. These are all kind of clumped, again, close-ish together. These are very far away. The diameters also, these are all relatively similar. These are all way, way bigger. The number of moons, notice the difference. And then we're going to get into talking about the days and the years and how that differs. But again, if we look back on Earth, just shy of 8,000 miles across, we have one moon. We're the only planet that has a single moon. Our rotation period, in other words, how long it takes our planet to spin around its axis, is just under 24 hours. So consider we have, leap year or leap days to account for the kind of the variance or the fact that a day isn't quite 24 hours and a year isn't quite 365 days. We kind of approximate those two things, but over time, we need to account for it. Right? So our day is just shy of 24 hours. And our year, obviously, is just a little bit more than 365 days. Okay? We know those things. Those are obvious. Now, let's look at the other inner planets. So we start with Mercury. Mercury is 36 million miles from the sun, so the closest by far. So 93 versus 36. It's the smallest planet, 3,000 miles across, and it has no moons. So think about that. Partly, that's due to the fact that it's close to the sun, and the sun's gravitational pull is so great, it's going to take away any opportunity for moons. And also, Mercury's mass is small, the smallest of the planets, so therefore its gravitational pull is the weakest. It has no moons for both of those reasons. Now, this is interesting. So notice Mercury's rotation period, or a day on Mercury. In other words, a cycle through daytime and nighttime, back to daytime, would take 59 of our Earth days. So even though Mercury is very close to the sun, it's spinning very slowly around its axis. So one chunk of a day, of what we consider a day, would be 59 of our days on Mercury. That means it would be light for, I'm approximating, but it'd be light for 30 days straight, and then it'd be dark for 30 days straight, and it'd be light for that, and that's what it would feel like. So it's rotating much slower, but because it's closer to the sun, its year is only 88 of our days. So a year on Mercury isn't much different than a day, right? A day is only 59, or a day is 59 Earth days, and a year is only 88 Earth days. So it's spinning much slower, but orbiting around the sun much quicker, closer in. Right now, I won't spend that much time on all these other planets. I just kind of want to drive home the point of what we're talking about. Venus is the next furthest out, 67 million miles away, 7,500 miles across, so very similar size to Earth. Venus also has no moons. A day on Venus is 243 Earth days. It's the longest day that we have in our solar system. And a year is 225 Earth days. So on Venus, a day is actually longer than a year, which is crazy, right, to think. So it would be, I mean, take 240, cut it in half. So 120 days straight of light and 120 days straight of dark, give or take, right? And during that time frame, Venus would have fully rotated around the Earth or around the sun and back and even more. So just interesting facts about how different some of these planets are in our solar system, how different and how similar in some ways, right? We went over Earth. Mars, 142 million miles away, so even further from Earth than Earth, 4,210 miles across, so much smaller, almost half the size of Earth. Mars has 2 moons. A rotation day or a rotation period or a day on Mars is almost exactly the same, 24 hours, 37 minutes, so very similar to the day we experience on Earth. But its year is 687 Earth days, which means, obviously, it's a longer period of time than the year on Earth. Now let's look at the giants, the gas giants. And I'll go through these, and then we'll get to some. Jupiter, our biggest planet, is 480 million miles away. So a huge jump from Mars to Jupiter. 88,700 miles across. So math on that, it's 11 times bigger than Earth. 11 Earths. Jupiter has 50 moons. 50 moons orbiting around. Partly because it's so giant, right? A day on Jupiter is only 9 hours in our time, like 9 hours and 51 minutes. So in 10 hours, Jupiter, even though it's giant, it's spinning so fast, it does a whole rotation around its axis in just under 10 hours. In terms of years, Jupiter takes almost 12 of our years to complete its orbit around the sun. Long. Saturn, same thing, is 0.9 billion miles away, 75,000 miles across, 53 moons, a 10-ish hour day, and almost 30 years, 30 of our years orbit around the sun. Now we're getting way out. Uranus, 1.8 billion miles away, 31,000 miles across, 27 moons, so not as big as Jupiter and Saturn, but still huge, right? A day on Uranus, 17 hours, 12 minutes, and it takes 84 of our years on one time. So some of us may not even live that long. 1 year. Neptune, 2.8 billion miles away. It's our furthest out planet. 30,000 miles across, 13 moons, 16-hour day. So again, you can see the similarities between the gas giants. And then a year on Neptune, or a rotation around the sun, takes 165 of our years. So when you really start to think about that, that's like mind-blowing, some of those differences. So with that in mind, and we're going to do some practice questions based on this, let's go ahead and try that. Go ahead and bore you to death with that long solar system explanation. So now we're going to have to do a little bit of jumping around. So kind of bear with me. I know it's not perfect. Number 1 says, according to the chart on page 534, so the chart we were just looking at, which of the planets takes the shortest time to revolve or complete its orbit around the Sun? Mars, Saturn, Neptune, Mercury. Okay? Now again, we're not talking about day. We're talking about orbit around the Sun. So we're talking about revolution period. Okay? So which one is the closest to the Sun? Which one orbits the fastest? Mars, Saturn, Neptune, or Mercury? And remember, the closest planet in, it would be the Mercury. All right. So here's an interesting question. Interesting in that it's kind of vague. According to the chart, which of the following planets is most similar to Earth? Mercury, Venus, Jupiter, or Neptune? Okay, so if we keep those in mind, Mercury, Venus, Jupiter, Neptune, let's look back here for a minute. Well, we know Jupiter and Neptune aren't very similar to Earth in distance, in diameter, in moons, in any way. So Jupiter and Neptune are the 2 I'd throw out for sure. The other 2 options, sorry, I have to scroll back because I have a bad memory, Venus or Mercury. So they make it easy on us by not giving us Mars and Venus. That would be a little tricky. So basically, we're left to pick between Mercury and Venus for which one we think is more similar to Earth. So all we can go by, because we only know the things that are on this chart, the only things on here are distance, size, moons, and how long days and years are. Right? So even though there are lots of differences between Venus and Earth, compared to Mercury, I would say Venus is the most similar to Earth. They're close together. They're almost the same exact size. They're similar in moons. Venus has none, Earth has 1. Their days are obviously much different, but their years are kind of close, right? Relative. So I would pick B, Venus, for that one. So here's the next one. So if we end a little early, we'll just, let's go ahead and do all of these questions. I think they're all. So hopefully you can read number 3 okay. I'll give you just a second to kind of go through it, and then I will read it also in case you can't see it. I'll give you a chance to kind of read it on your own for just a minute. All right. Take care of some business real fast, and then back to it here. So let me go ahead and read it for us in case you haven't already. Before 1781, the only planets that were known were the ones visible to the naked eye. In other words, the ones you could see in the night sky. Mercury, Venus, Mars, Jupiter, and Saturn. In 1781, William Herschel, an astronomer who made his own superb and powerful telescopes, discovered a strange star that appeared as a greenish disk rather than a point of light. A few nights later, he observed that this star had moved relative to the background of the other stars. Herschel realized he had actually discovered another planet. It was named Uranus after the Greek sky god. Later, it was found that Uranus had actually been observed at least 20 times before, as far back as 1690, but each time it had been identified as a star. So, see what they asked. The question asks us, which of the following is an unstated assumption that could help account for the fact that Uranus was misidentified as a star prior to 1781? So in other words, something that can be assumed but isn't mentioned, an unstated assumption. We've talked about this, I think, in class. I'm not going to harp on it. So let's look through our options. A, Uranus takes 84 Earth years to revolve around the sun. B, the length of a day on Uranus is about 17 hours. C, Uranus was not clearly visible with the telescopes generally in use at the time. Or D, Uranus was not visible on the other side of the sun. So the first two I would eliminate are A and B. We're not concerned with the amount of Earth years it takes the planet to orbit around the sun, and we're not concerned with the length of the day. In other words, well, we're not concerned about it in relationship to, does that account for why people would think that it was a star? No, that doesn't really matter. So it's clearly going to be C or D. And between these two, I would just go with what makes the most logical sense. Uranus was not clearly visible with the telescopes generally in use at the time, or D, Uranus was not visible when it was on the other side of the sun. Okay? I would go with the most logical answer. When I say most logical to me would be C, that it was not clearly visible because the telescopes at the time weren't powerful. So I would go with C. And I happen to know ahead of time that's C. But after guessing wrong yesterday or the day before, I had to redeem myself by making sure I knew the answer. It's fun to guess. All right, so let's look at number 4. I'm not gonna have us do this one, okay? According to the chart, which of the following planets has the most moons? That's just a matter of looking at the chart and reading. All right, we know Saturn. Easy question, and unfortunately, not something you're gonna see on the test. In terms of, you're not gonna see something that easy. So, by practice. Number 5. Let's look at number 5. We have time for both of these? Yeah, we should. So, number 5 says, according to some estimates, my screen was glitching out on me. According to some estimates, it would cost about 10 times more to send a crewed mission to Mars to collect geologic samples and look for life than it would cost to send a robotic mission. So, in other words, send people. Some people think a human mission would yield more relevant data, justifying the additional cost. Others think there is no scientific reason to send crewed missions, which are costly and risky when robotic missions will do. Which of the following values is most likely to provide the motivation to send a crewed mission to Mars despite the risk and additional? Which of the following values? And so basically, type of question you'd see on the reading test. So the content happens to be A, a desire to provide equal opportunities for astronauts of all nationalities. I don't see anything on there about astronauts of various nationalities. That doesn't seem, so I would throw that one out right away as I read it. B, a desire for economic development. Okay, I'm going to leave it for now. It's not popping out at me as being blatantly awful or wrong, so I'm going to leave it. C, a desire to demonstrate the superiority of computers over humans. That might be true if it was saying which of the following values is likely to provide motivation to send a robot mission instead of a crewed mission. But the question is the opposite. C is 180 degrees away from the logic that sending a crewed mission instead of a robot mission would accomplish, right? C is saying computers are better than people, so why would that? Those two things don't correspond, right? So I'm going to throw out A and C. So let's read D. We haven't even read D. D says faith in human judgment and decision making. So again, we're looking for what reason would someone that wants to send a human mission to Mars instead of a robot mission, why would that person say it's important that we send humans? Is it B, a desire for economic development? Or D, that they have faith in human judgment and decision-making skills? The answer here, the best answer, is D. Because somebody could say, well, yes, it's risky, and yes, it's going to cost a lot more, but having humans out there and having their judgment and their decision-making over a robot is going to be more valuable and ultimately provide more feedback than a robot. That's the values that those two things align, right? That value of human judgment and decision-making with sending a crewed mission over a robot. Those two things are compatible. And then the last question here, and this is kind of a bizarre question, but one that I kind of like in a way that it makes you think. So it takes what we talked about today and applies it to something totally different. It says the structure of the solar system, with the massive sun at the center and many objects revolving around it, is most similar to the structure of which of the following? A, the DNA molecule with a twisted spiral shape. So you've seen like a picture of a DNA molecule, right? Maybe like a twisted ladder. So does that sound similar to the structure of the solar system where you have a big, massive sun and stuff orbiting around? Not particularly. So A doesn't seem right. B, an atom with a dense nucleus and electron orbiting around the nucleus. So a couple words stand out to me as maybe potentially giving me a clue that this could be right. Dense and orbiting. We've got a dense center and we've got stuff orbiting around it. That sounds promising. Okay, let's look at the last two. C, the electromagnetic spectrum with waves of different lengths and frequencies. And D, the planet Earth with its layers of crust, mantle, and core. We talked about the Earth's layers. The way the Earth is structured doesn't sound like a dense nucleus. It's not like the crust is orbiting around the core of the Earth, right? So that D doesn't line up. And talked briefly about the electromagnetic spectrum, or like waves of different X-ray, gamma ray, like that kind of stuff. And things traveling in radio waves or in any kind of wave pattern doesn't sound like orbiting either, right? So the process of elimination, the best answer seems to be B. I realize as I've done this more and more and more, my tone kind of gives away the right answer, but bear with me. And hopefully going through the questions like this is somewhat helpful and can hopefully give you some ideas of how you might approach questions. At least that's my the reason why I go through the questions. So if you don't have any questions or you don't have any more comments or anything that we can go over, we'll go ahead and stop there. And we'll spend the last couple days of this week finishing up Earth and Space Science, and then it's on to Life Science, which is the one I saved for last because I don't like going over. But we'll get through it. So anyway, that's it for today. Have a good rest of your day, and I'll be back tomorrow for Social Studies and Science. All right. See you, everybody.